Logarithms are the study of inverses of exponential expressions. A logarithm is the inverse function of an exponential expression. So we're going to take a look at that first, and then we're going to look at the definition of a logarithm, and it's going to be a very important one to hear and to memorize. It's going to be a little bit hard to process. Let's go ahead and look at a problem. If I have y is a function of x, and it's equal to 4x, so this is the function I'm working with, then its inverse, again, replace y with x and replace x with y, is represented right here. And if I were to graph this fairly quickly, I'm going to throw these values up here on you. If I used a -2, -1, 0, 1, and 2 into this expression, I would get 1/16, then I would get 1/4, and 1, and 4, and 16 as outputs. And the graph of that would look something like this. And I'll stop with that ordered pair because I can't get the other one. So here's the graph of the exponential curve, y equals 4 to the x power. If I were to graph the inverse function, I'm going to put the table down here, I would end up picking values for y of a -2, -1, 0, 1, and 2. And then I would get out for that 1/16, 1/4, 1, 4, and 16. So I would come over here and I would graph that, and my first point would be here. X is 1/16, y is a -2, x is 1/4, y is a -1, x is 1, y is 0, x is 4, y is 1. And it's clearly the graph of an inverse function. To the graph y equals 4 to the x power, again, that's clearly the graph of the exponential function. The way we write this graph in logarithmic form is y equals the log of x where the base is 4. That is that same expression right here. And this is in words, and I'm going to read this to you. If this is called the inverse function, then I would say here that y is the power that I raise 4 to in order to get x. Yeah. So again, I'm going to write that down here. Y is the power I raise 4 to in order to get x. I'm going to put that in parentheses. That's the definition of a logarithm. Y is the power that I raise 4 to in order to get x, and that's what this represents right here. This is a formal definition for logarithms. We say that a logarithm is an exponent, and here it is as an exponent right here. Again, a logarithm is an exponent. This means that y is the power that I raise 4 to in order to get x. That's exactly what that statement means. Now, we're going to do some converting backwards and forwards and then some solving equations, and you'll see the practicalness of this. But at this point, you need to memorize, and probably a more non-commit, or I can't think of the word I want, is this form. Y equals the log of x where the base is a. A little bit hard to see, possibly. We'll go ahead and write the conversions up here on the next page that we work with. But again, the definition of a logarithm, it is an exponent. And it's the power that you raise the base to in order to get x. And it is, again, a logarithm is an inverse function to an exponential function. I put on the board the example that we left off with a minute ago. This was the inverse function that we had from an exponential function, y equals 4 to the x power. We wrote x equals 4 to the y power. We said then that the definition of a logarithm is an exponent, y, and it means here that y is the value, it's the value that I raise the base of 4 to in order to get this x. Now in more standard form, let me share it with you in that form. I would say, and I think I'm going to take this off the board in an effort to do that. If I have something in logarithmic form, and this is generalized form, where the log of x where the base is a is equal to y, that's how I might say that. The log of x where the base is a is equal to y, that I can convert that to exponential form. And remember that this is the power that I raise a to. So I would say this. That's the power that I raise a to in order to get x. That's a conversion, to go from logarithmic form to exponential form. Again here, y equals the log of x where the base is a. The base is a raised to that power is equal to x. And vice versa. Which one are we going to do first? Let's go ahead and I'll go ahead and put the vice versa on here. If I had a to the y power is equal to x, I could put that back into logarithmic form, and that is, a logarithm is an exponent, so that's always alone. It's equal to the log of x where the base is a. You just have to notice where you're going to put these. These are always represent bases, whether it's the base is an exponent or the base is a logarithm. So those values go in the same place. The exponent here and that, in this case, the y value are all alone. This x is what I'm taking the log of. These are the standard form. You must memorize these for this test. You must be able to convert from one to the other. So if I said to you, let's use this form. If I said to you, 10 to the second power is equal to 100, that's a true statement. But what I want you to do now is I want you to write that in logarithmic form. So what I do is I always say, okay, a logarithm is an exponent. So take the exponent and set it alone. That gives me my starting point. And then the base in exponential form, this 10, is the base in logarithmic form, and this 100 goes in the only spot that's left. I'm taking the log of 100, where the base is 10. It's equal to 2. If you took your graphing calculator right now and you hit the log key, then 100, and hit enter, it would give you an answer of 2 because your calculator is programmed to use a base of 10. That's a standard base. Now, we're not always going to use bases of 10. But your calculator, if you took the log of 100, it would give you 2. And it's because the calculator is thinking, she wants me to take 10 and raise it to some power to get 100. And 10 to the second power is 100. All right? Again, another one I want you to move from exponential form to logarithmic form. I have 10 to the 0.4771 power. That is equal to the whole number 3. If I were to write that in logarithmic form, the exponent is alone, and it's equal to the log of, here's my base, so it's the log of 3, where my base is 10, is equal to this. Again, your graphing calculator, if you took the log of 3 right now, it would give you 0.4771. And it's only because the graphing calculator uses a base of 10. We'll figure out how to use different bases later on, but we're not ready for that. If I gave you e to the negative 4 is equal to 0.0183, and I asked you to put that in just in logarithmic form, you would take your exponent, and it is equal to the log of your answer over here, 0.0183. And again, my base in exponential form is e, my base in logarithmic form is e. Now, if you hit the LOG key on your calculator right now, log of 0.0183, it would not give you a negative 4 because it would be using a base of 10. So be careful. The calculator LOG key only uses a base of 10, which is a common base. Again, be able to go from exponential to logarithmic form. And next, having done those 3 examples, let's go from, and so that was this formula right here. Now let's go from logarithmic to exponential form. So if I said to you, t is equal to the log of 9, where the base is 5, and I wanted you to put that in exponential form, I always look for my base first, and I want to raise it to the exponent power. Remember, that's the t because a logarithm is an exponent. That t is my exponent. What's left over is what this is equal to. In this case, 5 to the t power is equal to 9. Again, this is my x value right here, so right there I put that 9 in. Let's do it again. If I had, again, I'm just putting this one up a little bit backwards. So the log of 2, where the base is 10, is equal to 0.3010. And I wanted you to put that in exponential form. Here's my base, here's my exponent. The exponent's always alone. The log of something is an exponent. So I'm asking you basically to take 10 to the 0.3010 power, and if you did that, you should get this answer of 2. Okay? Again, my base of a, 10, to the y power, this 0.3010, equals that x value of 2. And if you took your calculator and took 10 caret 0.3010, you would get an answer of 2, and that's what we're doing right here. When we ask for the log of 2, we're wanting to know what the exponent is that you would raise 10 to in order to get that number 2. One last problem, like without numbers. If I asked you to convert or rewrite this in exponential form, I would take my base raised to a power. So m, base raised to a power, is equal to what I was taking the log of. I've gone from logarithmic to exponential form. You really, really need to be fast at switching back and forth in either form. Logarithmic to exponential, exponential to logarithmic. Our next objective is to solve equations, whether they be in logarithmic or exponential form. It looks like we're just going to solve logarithmic equations for right now by putting them in exponential form. So the first problem that I'd like to do is the log of x, where the base is 4, is equal to 3. I'm going to solve it again by putting it in exponential form. So my base raised to a power is equal to x. And I'm basically done. 4 to the third power is 64, so my solution is 64 for this problem. The log of 64, where the base is 4, is equal to 3 because 4 to the third power is equal to 64. That's it. I've solved for x. Let's do another example. I think I'll erase this one. Give you a minute. The next one that I'd like to look at is the log of 16, where the base is 4, is equal to x. And again, I'm looking to solve for x. So I need to put that in exponential form. So here's my base, here's my exponent. That means that I should write this as 4 to the x power is equal to 16. Now really, all I'm going to be asking you to do in this section is to observe, to see what the answer is. Well, what number do you have to put in there for x? To take 4 and raise it to some power and get 16, well, that's the value of 2, because 4 squared is equal to 16, and that's what I was looking for. I was looking for what power I had to raise 4 to. 4 to the second power would give me 16. I'm done. Here's my solution. And again, I'll give you a second. And the next problem I'd like to look at, again, solving equations, is the log of x, where the base is 5, is equal to 0. So there's the problem I'd like to solve. I'm going to put it in exponential form, so my base raised to a power is equal to, in this case, my unknown. But we know that anything raised to the 0 power is 1. And so I've discovered here that x is equal to 1, and the logarithm of 1 is equal to 0, where the base is 5. While we're at it, I'd like to discuss the logarithm of whatever, different base. Let's go with a base of 10. So I'm going to put this in exponential form. So I have 10 to the 0 power is equal to x. So I've got my base raised to this power. And it doesn't matter what your base is. Any base raised to the 0 power is always equal to 1. So it appears as though that I'm discovering one of the properties of logarithms, and that is that the log of 1 is always equal to 0. There are, good 6 properties of logarithms. This is one of them. The log of 1 is equal to 0, always. And that is because a base raised to some power, and if it has to equal 1, that's going to have to be the number 0 here. Any base raised to the 0 power will always give you an output of 1. So again, one of the properties, we're going to discover another property here, and then in the next sections we'll discover a few more. Here's one more problem I'd like to do. And that is the log of x, where the base is 32, is equal to 1/5. Now this one's a little bit tougher problem. I'm going to put it in exponential form, so I'll take my base of 32, and I'll raise it to the 1/5 power, and I'll let it equal x. Now when I raise something to the 1/5 power, that means that I want to take the 5th root of that. So I'm going to take the 5th root of 32 now, and then I will be able to find x, and then I say in my head, oh yeah, that's 2, because 2 times 2 times 2 times 2 times 2 is 32. In other words, 2 times itself 5 times. And so I've just discovered that the log of 2, where the base is 32, is equal to 1/5, because 32 to the 1/5 power is equal to 2. This is the last example that I'd like to share with you in terms of solving equations. And stop a minute, and we're going to look at some patterns. While we're going to be solving an equation here, I want to just look at a pattern that's going to result. If I take the log of a number that is a number in a multiple of 10, and the base that I'm using is a base of 10, I want you to see the pattern here. I am asking you to take 10 and raise it to some power, put it in exponential form, 10 to the x power, and have it equal 100,000. Well, it's 10 to the 5th power that is equal to 100,000 because 10 times itself 5 times will give you a 1 with 5 zeros. So we've just discovered that the log of 100,000, where the base is 10, is equal to 5, and it's equivalent, if you will, because the base is 10, to the number of zeros it has. So if I asked you to find the log of 10,000, you would probably tell me that that's equal to 4. Again, the base is 10, because 10 to the 4th power gives you 10,000, or 1 with 4 zeros. And this pattern continues. If I asked you for the log of 1,000, you would tell me that's equal to 3, because 10 to the 3rd power is 1,000. The log of 100, where the base is 10, is equal to 2, because 10 squared is 100. And finally, the log of 10, where the base of 10, is equal to 1. And this one right here gives me one of the next properties with logarithms. And that says that if I have the logarithm of a number where the base is the same, that I always get 1. And that's because 10 to the 1st is equal to 10. So if I said to you, what's the log of 4 where the base is 4, you'd automatically tell me that's 1 because 4 to the 1st power is equal to 4. So there's our next property for logarithms, and I've also put these in Course Compass under the supplemental or additional material from your instructor for this chapter. I put all the properties of logarithms in there, and one of them says that if you have the log of a number where the base is the same, that it's always equal to 1. Now here's the next thing. Get that graphing calculator out, and I'd like you to find, let's find the log of, with your graphing calculator, the log of, and I'm afraid I didn't write this one down, the log of 2,256, where the base is 10. Now the log of 10,000 is 4, and the log of 1,000 is 3. So when you hit on your calculator the log key, and then 2,256 and hit enter, you should get an answer of 3 point something, because I can see here that my answer must be between 3 and 4, since the log of 1,000 is 3, the log of 10,000 is 4, then the log of a number between those two should be somewhere in between those. Now I'm afraid I didn't do this one on my calculator, so only you could tell me what the answer to that is, but it's 3 point something. And that is the next thing that I'd like to just have you do. Now, since I can't check that one with you, would you just take your graphing calculator and would you check or find for me the log of 9,043,788. Now the base is 10, and if I don't write it there, it's understood to be a 10. We call that a common logarithm. A base of 10 is very common, so often you will see that we don't write that. And if it's not there, it's understood to be a base of 10. So if you type into your calculator log 9,043,788 and hit enter, you should get an answer of 6.9564, and that's because I expect this to be between 6 and 7 because of the number of places here, if you would. So that's how I'm sure that I got that answer. Here's another problem that you could check. Take the log on your calculator of 0.0067. Now that's a very small number, so I'm asking you to take 10 and raise it to some power to get such a small number. We're going to have to take 10 and raise it to a negative power in order to get that to happen, to get something so small as that. Again, check this out. If I were to check this, 10 to the negative 2.1739 is the same thing as 1 over 10 to the 2.1739. So I'm essentially taking 10 in the denominator and just about squaring it. And 1 divided by 100 is, something pretty small. So again, I'm just doing some estimates here to make sure that these numbers make sense to you. But this is all I wanted you to understand here was how to use your calculator. Hit the log key, hit the number, hit enter. log key, hit the number, hit enter, unless I go changing the base on you. If I had put an 8 here, this is no longer true, and at this point we don't know how to solve that problem. Here's an interesting problem. If I give you a number, 7, and I asked you to express the number 7 as a power of 10. So 10 to what power gives you 7? That's what I'm asking you. 10 to what power gives you 7? Well, the way you would get that, this is an exponent. And remember, a logarithm is an exponent. That would be gotten by taking the log of 7, where the base is 10, because I'm asking you to express it as a power of 10. So if you were given that number and you were asked to express it as a power of 10, I'm basically asking you to take the log of 7, where the base is 10. And so if you would do that with your calculator right now, the log of 7, where the base is 10, is equal to 0.8451. And so we would come over here and we would say 10 to the 0.8451 power is equivalent to the number 7. Very good. That concludes the opening to logarithms. Remember, a logarithmic function is an inverse to an exponential function. Remember that a logarithm is a power, and that I always am taking my base and raising that to that power to get what I'm taking the logarithm of. Be comfortable going backwards and forwards in each property, and we'll move on.